Greetings and welcome, friends. Today we are talking about modeling motion with matrices. Wonderful, wonderful. So you've seen all sorts of stuff to do with transformations prior to this, perhaps in some Math 2 or geometry equivalent class. And in today's class, we're going to represent two-dimensional figures in matrices, oddly enough. So here's a little sketch right here of a triangle on a coordinate plane, two-dimensional figure. And could you tell me what the coordinates of point A are? Where's A located? -2, up 4, right? So left 2, up 4, so this is the point, -2, comma 4. Here's point B. Where's B located? 0, comma 6, right? Yep. And point C is located at 1, -1. All right? So that's how you could represent any of those points. It turns out I can also represent this figure as a matrix. All right? And this is what's called a vertex matrix. All right? And I'm going to represent it. Let's see. Well, it's going to have to be have 2 dimensions for one of its dimensions, right? Because I've got 2 points for each of these. It turns out my vertex matrix is going to be a 2 by something matrix. In this case, it's 3 because there's 3 points I'm talking about. I wouldn't necessarily label the rows and columns, but what they would represent is the top row would represent the x coordinates. The second row or bottom row would represent the y coordinates. And then each column represents a single point. So it's possible I could have n many columns to represent n many points.
Can you scroll up a tiny bit?
Maybe. That's. I don't know. I can't. I've got. Come on, man. Come on. What is this, man? Come on, man. So in order to represent this, I'm going to have point A be the first column, point B be the second column, and C be the third column. But as I said, if I had a square or a pentagon, I could easily add more columns, but each row would always be the respective coordinates. So we'd have -2, 4 would be the first column, right? Then we'd have 0, 6, and then we'd have 1, -1. All right, so this is a vertex matrix. And it turns out I can use a vertex matrix to accomplish different transformations to the two-dimensional figure that it represents. All right, and this is actually how computer systems representing graphics or physical models of the real world would represent these things, where they would have points represented in a matrix, and then you could, animate those points by having different behaviors or operations take place to that matrix. All right. So just as a quick review, the types of transformations that can occur. Transformations that we're talking about. We've got a few of them. You can have translations. All right, which I don't know if you guys know what a translation is. I always get mixed up transformation, translation, because they both start with T. Oh, dear. Here we go. Bam. Aha. So here are the types of transformations. So a translation is a shift, right? So shift it up, down, left, right, sort of thing, or maybe a combination of the two. That would be a translation. A reflection, we've seen before, where you can reflect over a series of different lines. Reflections typically occur over the x-axis, y-axis, or something like that. So the x-axis is the equation y = 0. The y-axis would be x = 0. Or sometimes we might reflect over the line y = x. I know that the kids have heard that the scores are coming out, but that's all I've heard. Let's see, rotations. So rotations typically are about a certain point. We will often rotate specifically around the origin, all right? And the types of rotations we'll specifically deal with 90 degree, 180 degree, and 270 degree rotations, all right, is all that we're going to be concerned with today. And then there's the concept of dilations. Hopefully you've seen those before. A dilation, imagine if I had a triangle, and if I'm dilating it, all right, that means I'm scaling it up or down. So I could, for instance, map this triangle. So this point is now, say, 3 times as far away. This point is now 3 times as far away. This point is now 3 times as far away in that direction. And I end up getting a dilation, is what that's called. All right. And that's a dilation when you scale it up or down. All right. And you can kind of see like it would be something like that, right? Where it's scaling up or down, where each of these points is kind of shifting out or in along the lines that pass between those points, Jacob, or the origin of the graph. All right, so those are the types of transformations we're talking about. Let's talk about how we would accomplish a translation. Let's see here. Let's see. I'm going to grab a little snapshot of this. Nice little picture I drew up here. Bam. Snapshot. So let's do an example. Exemple. And I'm not going to have you draw this, but let's talk about this. So I've got 2 triangles. I've got triangle ABC. All right. This could be referred to as the pre-image. Okay. The location of my figure prior to the transformation. And then I've got triangle A prime, B prime, and C prime. And this is, as you might have guessed, called the image. Right, you don't have to draw the picture. We'll be able to represent this regardless. So I want to find a way to model, all right, a translation right 3 and down 2. So I'm talking about translation like this. So I went right 3. Let's see, is that actually 3 units? Did I miscount? That looks like right 2, huh? And down. Uh-oh, guys. You know what? You know what happened? When I translated this using my graphing software, it wasn't translating it by units. It was translating it by some dimension in terms of like inches or centimeters or something like that. Aha. So let's imagine this image the image is not fully translated over, but I desire to translate it right 3 and down 2. Okay? What we would do is first represent the original triangle as its vertex matrix. All right, so triangle ABC in its vertex matrix is going to be a 2 by, how big is this matrix going to be? 2 by what? 3, because there's 3 points. So I'll have point A go first. Let's see, so that's -2 up 4. I believe it's the same one that we might have just had. Yeah, 0, 6. And then I've got, what's that, over 1, down 1. So if I want to translate this, I want all of these points, all right, I want all of the x coordinates to have increased by 3, right? So the operation that I would do to accomplish that is I would add the following matrix. If I'm adding, what size does my matrix have to be? It's got to be the what? Same size. So it's also going to be a 3 by 2. And I want to add 3s to all of the x coordinates, so my entire top row would just be all 3s. And I want to do what to all the y coordinates? Yeah, I want them all to move down 2. So I'm going to add a -2 to all of those respective y coordinates. All right, so this is a translation matrix. And you can see that they have to be the same size. Right, and I merely add the translation matrix to it, and it's not that crazy. So triangle A prime, B prime, C prime is going to equal -2 plus 3 is 1, 0 plus 3 is 3, 1 plus 3 is 4, and then 4 minus 2 is +2, whoop, and then 4, and then -3. Right, so now I've got the vertex matrix for my image, and if I wanted, I could actually even break that apart into separate points of 1, 2, 3, 4, and 4, -3, if I wanted to find A prime, B prime, and C prime respectively that way. All right, so this, you're probably thinking, wasn't necessarily all that helpful. I mean, we perhaps could have accomplished that differently, or just, you know, even if they were represented as points, I could have just added 3 to all of the x coordinates and subtracted 2 from all of the y coordinates. And I would not disagree that that's not necessarily the most effective. But let's look at some of these other transformations. These ones are a little bit more interesting. Let's do an example here. Let's reflect using matrices. Okay, so let's see. Bop, 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 da, bop, bop. And this one, it looks like my graph came out correct. So, all right, so I'm dealing with triangles again. I'm keeping it simple for us. So the blue triangle is my pre-image. The orange triangle is my image. What type of reflection appears to have taken place here? Yeah, it's reflected over the x-axis, right? And what's the equation that represents the x-axis? Anybody? Equation of a line? Y equals 0, because all of the y coordinates on the entire x-axis are 0, right? Here's 2, 0, 3, 0, right? -π0. All of them have 0 as their y coordinate. So I want to reflect this over the x-axis. It turns out all I'm going to need to do is find the vertex matrix and leave some room on the left side of it, because we're going to have some room. So this is going to be a 2 by 3. Let's have, let's see, point A is -1, 1. So these tick marks, by the way, on this graph are representing half units. So here's -1, 1 for point A. Point B is over 2, up 1. So here's over 2, up 1. And point C is over 3, down 2. So 3, -2. All right, so here's the vertex matrix for our original triangle. And it turns out, now I've given you this little chart already that you've got, all right, of a series of matrices, and this is the top, what that top of that chart looks like, where if you want to reflect over the x-axis, there's a reflection matrix that we have, all right, that if I multiply this by it, it's going to give me the new coordinates of my image that are reflected over the x-axis. So this is the matrix that I'm going to multiply this by. Now question, first of all, would it matter what side I multiply this on, left or right?
Yeah.
Yes, it would, because you can't, multiplication for matrices is not commutative. And is it even possible to multiply this particular vertex matrix? If it was a square matrix, I'd be able to multiply it on either side, but it would still be wrong in one of those cases. But in this case, I just want to point out, if I tried to multiply this on the right, because this is a 2 by 3 and a 2 by 2, the inner numbers would not match, and it'd just be like frowny face. It wouldn't be happy. That was such a sad frowny face. It deserves a frowny face in response. So I'm going to take 1, 0, 0, -1, and multiply over here. Let's see. So 1, 0, 0, negative 1. And if I multiply this, well, actually, let's figure out what size answer are we going to get. Hopefully, it's still going to have 3 points and be a triangle by the time it's done. So let's see. This is a 2 by 2 multiplied by a 2 by 3. The inner numbers match. And my answer matrix, I'm expecting to be a 2 by 3.
Wait, where did you get the 1, 0, 0,
That's from the little chart that we have, the green sheet that I'd given you, where it says for a reflection over the x-axis, multiply by 1, 0, 0, negative 1. All right? So let's do this. All right, let's do this. So 2 by 3. First row, first column answer. Where does that come from?
First row, first column.
First row, first column. 1 times negative 1 is negative 1. 0 times 1 is 0. Bam. First row, second column. And actually, it's up to you if you want to find, second row, first column. I like to move horizontally. It doesn't matter as long as you're multiplying the right components. So let's see if I multiply first row, second column. That'll give me my first row, second column answer. So let's see, 1 times 2 is 2, plus 0 times 1 is 0. And then let's see, first row times third column is 3. And 0 times that is 0. What does it appear to be doing to my x coordinates compared to the original? Nothing. Exactly, Hank. Exactly. Notice, what do the x coordinates do? What happens to them when it goes from A to A prime? The x coordinates stayed the same, right? The x coordinates stayed the same here, and the x coordinates stayed the same here. All right? So it makes sense that this matrix is doing nothing to the entire set of x coordinates. All right? So let's do the second row here. So let's see. Second row, first column. This would be 0 and minus 1. This would be 0 and minus 1. And this would be 0 and plus 2. So let's see, negative 1, 2, and 3, and then I've got negative 1, negative 1, and 2. So question, what happened to my y coordinates? Yeah, they got opposited, right? These guys, all that happened to them was they done got opposited, right? And does that make sense? Notice that this y coordinate was negative 1, now it's positive 1. This one was negative 1, now it's positive 1. This one was, right, it went from negative 2 to positive 2. So that's exactly what happens when I have a reflection over the x-axis. All right. Now, would I have expected you to know that this matrix would have accomplished that? No. All right. But based off of what we see this 0 doing, we can see that that 0 ended up having no effect on all of those points. And we can see that this 0 ended up having no effect on all of those points. And the minus sign here merely changed this whole row's results. So, so it's kind of intriguing, all right, kind of unusual, but I want to point out that if you look at the y-axis one, what do you suspect is going to happen with if we had a multiplied by the y-axis? What do you think this top row would do? It would opposite all of which coordinates? All of the x coordinates, and this bottom row would do what? Nothing to all of the y coordinates. All right, so it makes sense, right? If I'm reflecting over the y-axis, all of the x coordinates get opposited, reversed, right? Negated, maybe, and all of the y coordinates stay the same. And if you look at some the other matrix, some other interesting behaviors happen. 0, 1, 1, 0 for the line y equals x. All that matrix is going to do is flip the x and the y. So you can use these matrices. One of the things I want to point out about, important note, is for reflect and rotate matrices, always multiply on the left side. Okay, and most of the time it wouldn't be a problem, but if you happen to have a square matrix where you're just reflecting like a line segment of 2 points or rotating a line segment, maybe it's not blatantly obvious. So that's worth pointing out. So let's see, let's do another example here. Oh, errors, friends, errors. Here we go. Example. Where is my mouse at? There we are. Exemple. Okay, here's my little sketch. My directions are going to say rotate the image 90 degrees counterclockwise. Hank doesn't like counterclockwise. You could rotate it 270 degrees clockwise if you want. It's going to accomplish the same thing. All right, so looking at this, first thing I'm going to have to do is find a vertex matrix that represents this figure. What size is my vertex matrix going to be here? 2 by 4. I agree. All right. The vertex matrix is always going to have 2 rows for the x and y coordinate, and then the number of columns is just based on the number of points. So let's see, point A is 1, 1. Point B is -2, 3. Point C is -2, 4. And point D is -1, 4. So here's our vertex matrix. Now let's see, we want to rotate the image 90 degrees counterclockwise. Turns out I've got a little matrix that's going to allow me to do that. It's going to be this guy. Right? So now once again, I don't expect that this is necessarily intuitive. All right? It could make a little bit of sense though over time. It turns out this matrix is going to switch the x and the y and make one of them the opposite. And that's going to be the same thing as a counterclockwise rotation of 90 degrees. So the matrix I want is 0, -1, 1, 0. And fortunately, all of these little matrices are square matrices, which is kind of good news. So 0, -1, 1, 0. So let's multiply on the left. All right, and just to explain what this is going to do, rotating about the origin. So here's the origin. I'm expecting this point. All right, if I find that distance, it's going to rotate 90 degrees that way. And these 2 segments are equal. So A prime I'm expecting to be somewhere over here. All right, except it's going to do that to all the points. So 90 degrees over here, you know, B prime is going to be somewhere over there. And this is going to accomplish the whole thing for us. It's going to be nice. So let's multiply. So I've got a 2 by 2 multiplied by a 2 by 4. What's the size of my answer? 2 by 4, hopefully. I like it. I like it. So let's figure this out. First row, first column. 0, -1. First row, second column. 0, -3. First row, third column. 0, -4. First row, fourth column. 0, -4. So it appears that the x coordinates are now going to be the opposite of the original y coordinates. Interesting stuff. And then the second row, first column, second row, first col, I'd have 1 and plus 0. Then I'd have -2 plus 0, and then -2 plus 0, and -1 plus 0. So these are the points: -1, -3, -4, -4, 1, -2, -2, -1. And each of these represent A prime, B prime, C prime, and D prime. And I intentionally did not graph the image on this picture. So let's plot these points and see if we agree with them. So negative 1, 1 would be over here, up here. So this is A prime. Then I've got negative 3, negative 2. So negative 3 down 2 right here. This would be B. It's claiming that that's a 90-degree rotation counterclockwise. I think we agree. Negative 4, negative 2. So negative 4 down 2. Okay, interesting. Interesting. And then we've got negative 4, negative 1 right here. So if I draw this, it would look something like this. And that's a 90-degree rotation about this point. All right, so that's our image. The blue shape is our pre-image. So one last concept, the easiest one. El más fácil del mundo. Yep, yep. Let's see, looks like I'm running out of room though with all my pictures. So let's see. Directions are going to say find the coordinates of the dilated trapezoid. All right. For a scale factor of 0.5. And I'm going to have to shrink this down a little bit to fit it. So, to do a dilation, all right, dilated is just kind of past tense verb of it. To do a dilation, remember that's just stretching it or smooshing it in all directions about the origin, okay, is what's technically taking place. So it's being enlarged or reduced by some factor. If my scale factor is 0.5, it's actually getting smaller. It's going to be half the linear dimensions, not necessarily half the area. I believe it's actually going to be a quarter of the area in that case. So what we're going to do is find the vertex matrix. So let's see, I didn't label these. Let's call this A, B, C, D. How about, why not, shall we? There we are. So the location of A is over 1 up 4, so 1, 4. B is over 6 and then not up or down, so it's 0. C is at, what is that, negative 3, negative 6. And D is at negative 4, 1. So it turns out, in order to do a dilation with matrices, we're going to take our scale factor of 0.5 and make it a scalar, almost. 0.5, I'm just going to multiply the whole matrix by that. And it turns out by halving all of the coordinates, it's going to half, one-dimensionally speaking, make this figure half the size. So what's this going to look like? 0.52, 3, 0, negative 1.5, comma, negative 3, and negative 2, comma, 0.5. And we might as well plot this just to verify. I'll do this real quick. You didn't necessarily have to graph this in order to do it, but I'll plot it just so you guys can see. So over a half, up 2, over 3, not up or down any, back 1.5, and down 3. Let's see, did I do that? Oh, there's 1.5, sorry. Over 1.5, down 3. And then back 2, up a half. And notice that if I draw this little figure here, it's a dilation of it where it's been scaled down by half of the original amount. All right, and I happen to have better than that. I've got the coordinates of all of those points if for some reason I had to do additional work to it. All right, so thanks for watching, internet friends. Have a great day. Bye-bye.